Hey, welcome. Today we are going to pull back the curtain on an invisible force that's responsible for everything from a crackling sweater on a dry day all the way up to a flash of lightning. Let's dive in. You know the feeling, right? We've all been there. You're walking across a carpet, you reach for a metal doorknob, and then zap. You get that tiny, surprising little shock. Or maybe you're pulling a sweater over your head in the dark and you hear that unmistakable crackle and see tiny sparks. So what on earth is going on there?
Well, the culprit has a name: static electricity. Now, static just means it's not moving. So what we're really talking about is electrostatics, the science of electric charges that are just sitting still. And today we're going to figure out how these stationary charges cause so much everyday mischief.
Okay, so to really understand that shock from the doorknob, we have to start with the absolute basics, the fundamental building block of it all, something called electric charge.
Think of it this way. Just like anything with substance has mass, it also has electric charge. It's just a basic property of matter. Everything, you, me, the air we're breathing, it's all packed with these charges. Most of the time, though, they're perfectly balanced out, which is why the world doesn't feel all zappy. Most things are electrically neutral. So, it turns out charge isn't just one thing. Through some pretty simple experiments, like rubbing different things together, scientists figured out there are two distinct types, and it was actually the American scientist Benjamin Franklin who gave them the names we still use today, positive and negative. It's really just a convention, but the charge you get on a glass rod when you rub it with silk, we call that positive, and the charge on a plastic rod rubbed with fur, we call that negative. And right here, this is it. This is the single most important rule in all of electrostatics. It's super simple, but it is incredibly powerful. Charges that are the same, so two positives or two negatives, will always push each other away. They repel. But if you have two charges that are different, one positive and one negative, they will pull toward each other. They attract. This simple push and pull is behind literally everything we're about to talk about.
Okay, so if most stuff is neutral, how do objects get that extra charge that leads to a spark? I mean, where does it even come from? Let's take a look.
Now, this is a really crucial point. We are not creating charge out of thin air. It's not magic. When we say something is charged, all we mean is that we've unbalanced it by moving tiny negatively charged particles called electrons from one place to another. So, if an object loses some of those electrons, it's left with more positive charges than negative ones, and we see it's positively charged. And if it gains extra electrons, well, now it's negatively charged. It's all about moving electrons around.
And there are basically three main ways this electron swapping happens. The first is friction. That's exactly what happens when your shoes scuff on the carpet. The rubbing literally scrapes electrons from one surface to the other. The second way is conduction, which is just a direct transfer of charge by touching. And finally, there's induction, which is super cool. It's a way to charge something up from a distance, without any physical contact at all.
So we know that charges either attract or repel. But can we measure how strong that push or pull actually is? You bet we can. And that brings us to one of the foundational laws of physics. For this, we need to meet the French physicist Charles-Augustin de Coulomb. Back in the 1780s, using this incredibly sensitive device called a torsion balance, he was the first person to actually precisely measure the force between two electric charges.
And what he discovered is now called Coulomb's law. It sounds complicated, but the idea is actually pretty simple. First, the more charge you have, the stronger the force. That makes sense. But, and this is the really important part, the force gets weaker very, very quickly as you get farther away. So if you double the distance between two charges, the force doesn't just get cut in half. No way. It drops all the way down to 1/4 of what it was before.
We're almost there. There's just one last piece to our puzzle, and it answers a really fascinating question. How does a charge over here feel another charge all the way over there?
I mean, really think about that. There's no string connecting them, nothing you can see. So what is the messenger that's carrying this force across what seems like empty space?
Well, the answer is that every single charge actually changes the space around it. It sets up this kind of invisible web or an area of influence that stretches out in all directions.
This area of influence has a name: the electric field. And it's not just a clever mathematical idea, it's a real physical thing. When you bring a second charge into this field, it's the field itself at that specific point in space that pushes or pulls on the new charge. That's how they communicate without ever touching.
All right, so now that we get the idea of fields, we can look at a really common and super important arrangement of charges that you see all over the place in nature. It's called an electric dipole, and it's exactly what it sounds like, a pair of charges. You have one positive charge and one negative charge of the exact same strength, held just a small distance apart from each other.
Now you might be thinking, wait a minute, a positive charge and a negative charge, don't they just cancel out to zero? And you're right, the total net charge is zero. But here's the kicker. Because they're separated in space, their electric fields don't perfectly cancel out. And this is a huge deal. Tons of molecules in nature are dipoles, and the most famous example of all is water. An H2O molecule is a natural permanent dipole, and that one fact is responsible for almost all of water's weird and wonderful properties.
And with that, we've done it. We have all the clues. We have friction, conduction, attraction, repulsion, and fields. So let's put it all together and finally solve the mystery of that doorknob zap.
So here's the step-by-step. As you walk across that carpet, friction is scraping electrons off the carpet and onto you. Your whole body builds up a net negative charge. So now, you're basically a walking, talking, charged-up object. That metal doorknob is what we call a conductor. It lets charge move through it super easily. So when your charged hand gets close enough, all those extra electrons on you see a great escape route. They leap from you to the doorknob to balance themselves out, and that tiny rapid flow of charge is the spark you see and the shock you feel. Mystery solved.
You know, that little shock is really just a tiny glimpse of a much, much bigger picture. As this quote says, the electric force is everywhere. It's the fundamental force that holds atoms together to create molecules. It's why glue is sticky. It's what powers so much of our technology. From how a photocopier works to how industrial smokestacks can scrub pollution from the air, it's all electrostatics.
So I'll leave you with this thought to chew on. We've really only scratched the surface today. If this invisible force is powerful enough to hold the very building blocks of matter together, what else in our world, from our own biology to our most advanced computers, is secretly being controlled by these simple, fundamental rules of attraction and repulsion? Thanks so much for joining me.